my YouTube channel. So let's continue with the molecular orbital theory part 4. So in this part 4, we will discuss about the homonuclear diatomic molecules. So we have two main objectives for this part 4. First one is to discuss about the bonding in the S block homonuclear diatomic molecules, and second one is the molecular orbital from atomic p orbital combination. So how to draw how to show the bonding in the S block homonuclear diatomic molecules? For the first one, you need to show the valence electron, only the valence electron for that element. Okay, so in this example, we have lithium 2. Okay, so the proton number for lithium 2 is 3. So the electron configuration for lithium 2 for the lithium is 1s2 and 2s1. Okay, so here, because we have a lithium 2, alright, so the electron configuration for lithium is 1s2 2s1. Okay, so the valence electron is here, okay, located at 2s1. So you only need to show the valence electron here. So we have one orbital of 2s1 and another one is 2s1 because we have lithium 2 here. Okay, right, and then because we are dealing with the S, so we only have the sigma 2s. Okay, so this is the sigma 2s and also sigma star 2s. Okay, so how many electrons? Okay, so you need to add on, okay, on your left side and also on your right side, okay, or the sum of electrons from the atomic orbital of the lithium. So 1 plus 1, we start to include, or we start to add on the electrons from the bottom to the top. So 1 plus 1, we're going to have a 2 here at the molecular orbital of L12. So don't forget to label, okay, this is the atomic orbital of lithium and this one also atomic orbital of lithium. From this molecular orbital, we can determine the lithium 2 bond order. Okay, so the formula is half minus the bonding electrons here minus with the non-bonding 0, so it will give us the bond order of 1. So here, this is the lithium 2 Lewis structure. What about, let's say we have a beryllium 2? Okay, so for the beryllium 2, beryllium is 4. Okay, so 1s2 and 2s2, and the electron configuration here is the 2s2. Sorry, the valence electron located at beryllium here is at 2s2. So we have the atomic orbital of beryllium and this is also atomic orbital of beryllium, while at the center one we call it as MO, molecular orbital of beryllium 2. So here, okay, we have the sigma 2s and also sigma star 2s. Okay, so you need to add on this side and also this side. So 2 plus 2 will give us 4. And please remember that maximum number of electrons in one orbital is only 2. Okay, alright. So one orbital maximum we need to have 2. Okay, so this is the half and this is the negative half. Okay, alright. So from this molecular orbital, we can determine the bond order. So the bond order here is half times 2 minus 2. So it will give us 0. So it means here that beryllium 2 does not exist. Okay, alright. So what about the molecular orbital from the atomic p orbital combination? Let's say we have anything related to the p orbital. For example, oxygen, carbon, nitrogen, fluorine, and so on. Okay, alright. So we need to have the shapes and also energy of molecular orbital form from the combination, and then we have two kinds of overlapping here. Okay, similar to the hybridization, the end-to-end, okay, the end-to-end overlapping, okay, pair of the sigma molecular orbitals. Okay, so this one will involve in the px. Okay, it's the px orbital here. This is the shape of the px. Okay, where it will form the sigma 2p and also sigma star 2p, and then this is the first one. And second overlapping here, we have side to side, okay, that will form a pair of pi MOs, okay, which are the pi 2p and also pi star 2p. So this one will involve with the py and also pz. Okay, alright, so py and also pz. Okay, alright. So and then here, other than that, bonding of molecular orbital has greater electron density between nuclei, so it will have less energy. Okay, while for the anti-bonding MOs has node between the nuclei, okay, where we have a zero probability to find electron. Okay, and what happened here, their electron density outside internuclear region, and they are going to have high energy. Okay, high energy because of the because the electrons, okay, the electrons do not shield the nuclei, okay, or the nucleus. So what happened, it will increase the repulsion. Okay, that's why this anti-bonding always has higher energy. So what about the orders of energy level? Because we are dealing with the sigma and also pi. Okay, 2s, okay, 2s are lower energy than 2p, and bonding MOs lower than anti-bonding MOs. Okay, so it means that end to end and then followed by side to side. Okay, and the energy order here, we start with the sigma 2p and then followed by pi 2p and then pi star 2p and also sigma star 2p. Why we have this kind of arrangement? Okay, because the sigma 2p here, okay, has higher energy because of destabilizing effect, okay, that greater than the pi star. So for the destabilizing effect, I will explain more this one during our virtual class. Okay, alright. So other than the arrangement or the energy level, you need to know the shape. Okay, what happened when we have a side-to-side overlapping and also end-to-end overlapping. Okay, let's look at the first one. This is where we have end-to-end. Okay, where we have the overlapping between px and also px orbital. Okay, so we need to add and also subtract. Okay, if we add these two px, okay, orbital, what happened here, it will form a sigma 2p MO, where we have a bonding here. Okay, a bond here. So the electron density will become higher at the center. Okay, alright, or at the nuclei here, surrounding the nuclei. And if we subtract, okay, these two, okay, alright, so what happened here, it will form a node. Okay, okay, it will have a node here where the electrons move towards outside, okay, the region of this node. Okay, and it will form a sigma star 2p where we have an anti-bonding. Okay, that one is for the end-to-end. What about, let's say we have a side-to-side. Okay, so this is the side-to-side overlapping. Okay, when we add both of these, okay, it will form a pi 2p, or usually we call it as a pi bond. Okay, so the electron density will be higher here. Okay, alright, and if we subtract of these two side to side, it will have a node here, and then it will have this kind of shape. Okay, where the electrons try to escape themselves from the node, and it will form a pi star 2p, okay, which is an antibonding. Alright, okay, so here, okay, this is also similar explanation, okay, from the previous slide. Okay, this is where we have a destructive and constructive, or bonding and anti-bonding, and also from end to end and also side to side overlapping. Okay, alright, so let's go for the first one. Let's see what we have if we okay, here for the second period homonuclear diatomic molecules. Okay, usually we focus on the oxygen O2, fluorine F2, and also Ne2. Okay, so how to draw this kind of molecular orbital diagram for these three molecules? Okay, so for the first one, okay, we need to show their valence electrons. Okay, alright, so all these three will have the p orbital. Okay, so the px, y, and z. So here we have energy. For the first one, you need to have energy. Okay, you need to draw the energy. And then second one, you need to have the p orbital both side, on your left and also on your right, because this is the atomic orbital, atom. Okay, alright, and then at the center here, you're gonna have the molecular orbital. Okay, where we have the O2, F2, and also Ne2. So at the center here, we start with the sigma 2px, and then followed by the pi 2py and pi 2pz. Okay, or you can write it down as sigma 2p, okay, pi 2p, and also another one, also the pi 2p. Okay, alright, and then after that, we gonna have the sigma star 2p, and here, alright, and also this is the pi star 2p, and also followed by the sigma star 2p. Alright, so for this one, you need to make sure that your left and also your right side, okay, the orbitals here, okay, both of these equals to this. Okay, so we have 1, 2, 3, 4, 5, 6, and at the center here for the molecule, we have 6. 1, 2, 3, 4, 5, 6. So this is the arrangement for the oxygen, fluorine, and also neon. Alright, and okay, here, alright. So in this case, for O, F, and also Ne, the orbitals do not mix, okay, because of the size of atoms are small, and the relative strong repulsion rays energy of 2p, okay, orbitals are high enough to minimize the orbital mix. Okay, alright, so and last one, okay, this is number 2, and this is number 3, and number 4, you just need to fill up the electrons, okay, from the atomic orbital here, and fill up in the MO here. So this is the atomic orbital of O, F, and E, and this is also similar, the AO of O, F, and also Ne. While for this one is the MO, molecular orbital of O, F, and also Ne. Okay, this only apply, okay, this is only apply on the small atom, okay, on the small atom. Okay, the arrangement is 1, 2, 2, 1. Okay, so what happen if we have a big ataupun a larger molecule, okay, where usually the B2, boron 2, carbon 2, and also nitrogen 2, okay, so they have a larger ataupun large size. Okay, alright, for the first one, you need to have the energy. Second one, you need to have the atomic orbital, okay, on your right and also your left side. And then you need to have the molecular orbital. Okay, so the arrangement for this B, C and also N, because they have a large size, it will start with the pi first. Okay, not the sigma. The pi here, and then the sigma, and then pi star and also sigma star. Okay, alright, because of the large size of this, we're gonna have this kind of arrangement. Okay, and these orbitals do mix because of the size atoms are larger. Okay, but the previous one, they do not mix. Okay, and the atomic orbitals are usually a half field, relative small repulsion makes the 2s and 2p orbital much closer and orbital mix occur. So okay, this is how you need to draw on for the molecules boron 2, carbon 2 and also nitrogen 2. So let's look at the difference between this mixing and also without mixing. Okay, so for the first one here, okay, this is the small size. Okay, small size of molecules. Okay, so this we call it as without 2s 2p mixing, where the arrangement here we start with the, this is the 2s, okay, level, while for this is the 2p level. Okay, right, this is the 2p, this is the 2s, because we need to show the valence electron. Okay, so for the difference here, okay, is the arrangement of the 2p. If we have without 2sp mixing, we start with the sigma, pi, and then pi star and sigma star, while if we have the mixing, sp mixing for the large size, okay, we start with the, for the 2p orbital, pi 2p, sigma 2p, and then pi star 2p and sigma star 2p. Okay, alright, so this is what you need to have, okay, or what you need to show in order to draw the molecular orbital diagrams. Okay, so the difference is here. Okay, the main difference is here. And then other than that, okay, this is similar. Okay, and also this is the 2s. Okay, alright, and the energy order, this is general. Okay, this is general on energy order, sigma, and then followed by pi, pi star, and also sigma, sigma star. Okay, so other than that, okay, from this molecular orbital, okay, other than the shape, okay, you need to know the HOMO and also LUMO. Okay, HOMO and also LUMO. What is HOMO? HOMO is highest occupied. Highest occupied molecular orbital. This is a HOMO, where you need to find the highest energy of an electron, minimum 1 electron in this molecular orbital. Okay, that one can be considered as HOMO, while for the LUMO, okay, is the lowest unoccupied. Unoccupied molecular orbital. This is LUMO, where you need to find an orbital, okay, with no electrons, okay, with no electron at all at the lowest energy level. Okay, alright, so you need to okay, you need to draw, and then from this molecular orbital you can determine the bond order. Other than that, you can determine the HOMO and also LUMO. Okay, so these are the shapes, okay, of the orbitals overlapping. And then other than that, okay, here we also need to determine the HOMO and also LUMO. So we will discuss this later during our class. Okay, I will show you how to determine the HOMO and LUMO. Okay, alright. And then this is the SP mixing, okay, for the large size of molecules. Alright, so that's all for today. Okay, thank you everyone, and thank you for joining me, and thank you for spending your time in this part 4. Please don't forget to like, comment, and also subscribe to my YouTube channel. So I'll see you guys in part 5. Bye.